Last lecture, I started to talk about magnetostatics, so where we really considered the stated currents and what is the magnetic field that are produced. And of course, we expect the magnetic field to be constant because the currents, in the problems, in the configurations, they are steady. Okay, so we may talk about a question like this. So let us say there is a loop and there is a current first flowing through the wire, and we talk about a small distance dl prime here, and we wanted to figure out what is the magnetic field, that is the distance r here. Okay, to calculate that, we can define this cursive r as the separation vector between this element of length and the final position we wanted to calculate the magnetic field. And we mentioned that we have this Biot-Savart law, okay, which is equivalent to the Coulomb's law in electrostatics. So here, this law, it says that to calculate the magnetic field at this position r is equals to mu 0 divided by 4 pi, and then we have this integral, okay, which is really I dl prime times this cursive r direction divided by cursive r, the magnitude square. Okay, so of course, the problem that we want to handle is a stated current, so you can move this I outside, so that's okay. And from here you can see that it's also a vector equation, and we also have this 1 over this this is basically r square. So this is also have this 1 over r square dependence. So it means if you are far away from this loop of current, and then the magnetic field will become smaller. Of course, we can also do it. So this is for what I assumed here is for the line for a wire carrying current. We can also talk about the field, the two-dimensional surface one. So we also have this K. What we mentioned is the surface current, okay, at a position r prime times this r hat cursive r hat times this dA of dA prime, okay, because it's a surface integral. And this is what we have, for the volume integral, where we talk about a volume current density. So we have J here, which is r prime, times r hat and r cursive r square, and times to do the volume integration, which is d tau prime. Okay, so this is what we have. Okay. Okay, now just like Coulomb's law, I wanted to show you a few examples and how to use this Biot-Savart's law to calculate the magnetic field. And we will do it for a few interesting examples. You can see that how we can use it to do the calculation. So now the first thing is, let us say I have one example here. Now we have a single wire here, okay, that carries a steady current I here, okay. Now we have a magnet. We have a point here, okay, that has a distance s, okay, that away from this current, from this wire, okay. We wanted to figure out what is the magnetic field B value here at this point P, okay. Okay, to do that, of course, this is we can consider the small element of length, Let us call it dl prime here. Okay, and then we need to calculate the cursive r direction. Okay, which is just the distance between this small element and the position that we want to calculate the magnetic field. Okay, and we can also figure out the direction of the magnetic field. And you see the current, let us say, along the x direction, and r hat is kind of, if you think the plane is xz plane, and then you use the right-handed rule, you will see that this dl prime cross this cursive r head should be pointed out of the page, which is really the y direction, positive y direction. If no, it's negative y direction. Okay, if we define this as x, the pointing, this is y, so this is z. Okay, so it's just the negative y direction. Okay. Okay, so the magnitude, this dl prime times this r hat. Okay, so this one is really just because if we consider this angle to be theta. Okay, so this is theta, and this one, okay, so this one is a half pi minus theta. Okay, so this one of course is pi minus theta. So this is a pi plus theta. Okay. Okay. So this one is really now the magnitude of this, of course, is just the same, the area that are covered by these two vectors. So this is becomes dl prime times this same pi plus theta. Okay. So this one, if you do it, is this really times cosine theta. Okay. So this is what we have. Okay. For the magnitude of this cross product that we wanted to calculate here. Okay. Once we have this, we can try to plug into the formula. Okay. So we wanted to use everything, we use theta. Okay. So that later we can use theta to tell us the range, the length of this wire. Okay, so now we have this, and we also convert this dl and dl prime, and we will try to use theta to indicate that. So what we have is, if this length is l prime, so we have l prime is really equals to s times tan theta. Okay, from here you can get a dl prime is really s divided by cosine theta square d theta. Okay, so in other words, that we just replace it, these things with theta now. Then we also need to change this cursive r. Okay, and we replace it with theta. So what we have is this cursive r times cosine theta. Okay, give us this s, this height. Okay, from here, of course, we can get cursive r, 1 over cursive r is really cosine theta square divided by s square. Okay, so now we can plug this into the formula. Okay, this is BS formula. Okay, divided by 4 pi, and we want to depends on the wire position. Okay, the length of the wire. Okay, the it could be from this length to this length, for example. Then what we really, the first angle is theta 1 here, and then this length, it will be theta 2. You just cover in that range. Okay, we just plug into this s square times this dl prime cosine theta. So this is really cosine theta square. Then we have another cosine theta d theta here. Okay. Okay, so you can see that cosine theta square cancel the s, also cancel the 1. So what we have is mu 0 I divided by 4 pi s. And we have sine theta 2 minus sine theta 1. Okay, so this is what we have. Okay, if a wire, okay, that has finite length, okay, that carries a steady current I, and we can calculate the magnetic field that is a distance s away from this wire. Okay, now we can consider this infinite wire. Okay, the length is infinite long. Okay, so for that case, theta 1, what we have is minus pi over 2. You can see that it goes to infinity. Theta 2 will just goes to pi over 2. Okay, from here you can see that this b now is just simply becomes mu 0 divided by 2 pi s. Okay, so this one will give us plus 2, and it will cancel with 2, so you get a 2 pi s here. Okay, and also we know that by the using the right-handed rule, we know that the field is really loop around this wire. Okay, so we really know that the B field direction for this infinite long wire is mu 0 I divided by 2 pi s. That is along along the phi direction, around the wire. Okay, so now you can see that here is how we find out the magnetic field along an infinite long wire. Okay, so now what we can do is we consider two wires. Okay, they are both very long. Okay, one is I1, one is I2. So what we do is we first find out the magnetic field around I1. So we know that it should be circles around this wire. So now you can see that at this I2 position, okay, the second wire, the B field there is really mu 0 I1 divided by 2 pi d. Okay, let us assume the distance is d. Okay, so this is the magnetic field there. Okay, now we really wanted to calculate the magnetic field force, the Lorentz force. Okay, to do that, we have to look at the formula that we have before. Is really I2 times dl across b. Okay, and we said that the current is along this direction, and we said is parallel. If they have same current, then the force is really attractive force. Okay, so F is really that way. Okay, and this force really can be calculated really as I2, and B value is really a constant, 2 pi d. Okay, just times dl. Okay, depends on the length of this wire. Okay, that are inside this magnetic field. Okay, and of course, if we wanted to calculate the magnetic force per unit length. Okay, this is just so that we don't need to worry about the length of the second wire. So this F, of course, is just mu 0 times I1 I2 divided by 2 pi d. Okay, so this is really the length. Now we just do it per unit length, so that really this one becomes 1. Okay, so here is just how we calculate the magnetic field force between two wires. Basically, you first figure out the magnetic field, and then you plug into the Lorentz force formula that I described before. Okay, so you can see that we really start from this Biot-Savart law to figure out the magnetic field around a wire, and then you see to calculate the force between two wires. Okay, now let us look at another example. Okay, just to use examples to show you how to use this Biot-Savart law. Okay, so now let us consider this case. Let us consider there is a loop. Okay, that is has a circular shape and has a radius which is r. Okay, and now there is some current I that are flowing through this wire. Okay, and now we want to figure out the magnetic field here. Okay, that is distance z away, the point P, that is distance z away, okay, from the wire, okay, from the plane of this wire. Okay, so now how to really do the calculation. Okay, the way to do that, of course, is really just to use this this law. Okay, this is really I dl prime cross this cursive r direction, cursive r square direction. Okay, so now of course really here we need to, the difficult part of course is really to figure out this direction and this direction. Once you figure that out, the rest is just some calculations. Okay, so the way we do it, of course, is we, here you can see that it's better to use this cylindrical coordinate system. Okay, so now we consider dl prime is this way, and you see that the dl prime, okay, which is certainly, that is along the phi head direction. So we have s phi z. We use these three coordinates, and we know that the length is really the radius really r, okay, times d phi, and the position is really along the phi head direction. Okay, so you need to figure that out. Okay, so this is what we have. Okay, for dl prime. Now let us figure out what is the cursive r. Okay, so this cursive r, and you see that is really a vector like this. So it's really this vector plus this vector. Okay, and we can get this cursive r direction. Okay, and this one we know that is really a vector, okay, which is really minus r s hat. Okay, is the radial direction, but it pointing from outside to the origin. Okay, so it should be minus r s hat direction, and if this is O, and the OP direction, of course, is really z hat direction. Okay, so here is how we calculate this cursive r direction. Okay, so once we have that, this one, of course, we can, for this one, we can really let it write it down as times this cursive r, okay, then divided by cursive r cube. Okay, I just replaced this unit direction really with this, because it is really equivalent to this. Okay, so now once we put it together, so we have dl prime times this cursive r direction. Okay, and of course, phi hat cross s hat will give you phi hat cross s hat will give you negative z hat direction. Okay, so I just, you because it really S hat is this direction, phi hat is this direction, and z hat is this direction. Okay, they are also perpendicular to each other. So you just do the cross product, and you get this RZ and d phi S hat plus R squared d phi Z hat. Okay. And then we can calculate this one will be really RZ d phi S hat plus R squared d phi Z hat, then divided by this is the length is really Z squared plus R squared. We see this. Okay. So now you just need to do the integral. Okay. The z hat direction is fixed, but you have to remember this s hat changes direction. For different points, they are different. So we know that s hat is really cosine phi x hat plus sin phi y hat. Okay, it's just the radial direction. Okay, so now if you do the integration, and of course we will integration this phi angle from 0 to 2 pi, and then you will find that you basically need to cosine phi d phi. Okay, you will find it equals to 0. Then the same thing for this sin phi. When you integrate phi from 0 to 2 pi, you get 0. So in other words, that the first s hat interaction will give you 0. Okay, it is only the integration that are left is only for the z component. So in other words, that what we really have, I put an I outside. What we really have just this r squared d phi divided by z squared plus r squared, only along the z hat direction. Okay, and this will integrate from 0 to 2 pi, and of course this will be cancelled with this 4 pi. We are left with 2 ui divided by 2. Okay, and then all these, they are constants, z squared plus r squared 3 over 2. Okay, it's along the z hat direction. Okay, so this is what we have. Okay, for the magnetic field that are at this point 2. And you can also use symmetry reasons to understand that the magnetic field has to pointing, okay, along the z direction because of all the symmetry reasons. Okay, if you do integration here, there is a corresponding length of segment that are on the other side, that will cancel the xy components, for the B field. Okay, so that at the end you only have the z component left out. Okay, now once we have this, let us like what we did for the electrostatics. We wanted to look at the divergence, okay, for the magnetic field, and we also look at the core of the magnetic field and see how they look like. Okay, so now let us look at something easier. Look at a straight line. Okay, you will see it is much easier. So we will look at a straight line currents first. Okay, so we really, let us say I have a straight line here. I have current coming through, and we know that we expect the magnetic field to be curved around this wire, and the way to do the calculation is really, if we have the B dot dl. Okay, so the B is really, as I said, if this is infinite long, and we expect the field to be mu 0 I divided by 2 pi s. So this is really the integral of mu 0 I divided 2 pi s times this dl. Okay, for this case, if it's a circle, okay, if it's the distance is s away from this, so this is a constant we move outside, the dl just give us 2 pi s, which is the circumference of this circle. Okay, so this give us mu 0 I. Okay, and you can see that this one, we do the line integral, and we get mu 0 times the current, okay, that is enclosed within this loop. Okay, and now if you do the integral, if you have I here, if you consider a loop, okay, that is outside, okay, it doesn't include this I, okay, this current is not within this loop. And what you do is you really do this dl, and of course at each point, this field is different. However, when you do the integral, okay, and that it goes from originally is phi 1, it also needed to go back to the phi 1, okay, because this is a closed path, and you will find that the b dot dl is really 0, okay. So in other words, that if we wanted to integrate a loop that doesn't include any current inside, then it will becomes 0, okay. And here the conclusion what I showed here, it doesn't really, here I just assumed it is really a circle. It doesn't really need to be a circle. And you can really demonstrate that the main reason is because our B field is, as I said, is along the phi hat direction, okay. And if we assume dl, we can write it down in this in this cylindrical coordinate system. We have ds s hat plus this is s d phi hat, and dz z hat. Okay, we have this the change of this vector. Okay, so if you do this b dot dl, at the end you can see that is mu 0 I divided by 2 pi s times s d phi. Okay, so this one cancels mu 0 I divided by 2 pi d phi. Okay, so you see from here, if this is a closed circle, if this closed circle circulate, enclose this current, then the phi will be integrated from 0 to 2 pi. Okay, if this one doesn't include the current, you start with some value and then you go back to that value. So this the integral, okay, is really becomes 0. Okay, so that is what we found. In other words, we can really summarize these two equations together. It becomes mu 0 times I enclose. Okay, so this is really just the total current. Okay, that is enclosed, okay, by this loop, by the integration loop. Okay, so this is what we have. Okay, and then you may see that this is very similar to the Gauss's law that we have. We have this E dot no. Okay, so this really we have E dot ds. Okay, that we have include the charge divided by epsilon 0. Okay, So here we just do, here is the surface integral, and here we are doing the line integral. And we found that the line integral is really proportional to the total current enclosed by the integration loop. And here we are really have, the surface integral equivalent to the amount of charge that are enclosed inside, that surface or volume. Okay, so this is what we have. Okay, so this is really called Ampere's law. Okay, this is equivalent, to this Gauss's law in this electrostatics. Okay, and this is the integral format. We can also look at, of course, if there are two wires, let us say, okay, I have another current, I2, for example, that also pass through this loop. So in that case, my I enclosed should be I plus I2. Okay. So this is an integral formula. Then we also wanted to figure out the differential formula. So what we have is really, we know that, the enclosed current really is the density times dA, the volume current density times the area. Okay. So in other words, that we can write it down this integral format is really mu 0. This one becomes J dot dA. Okay, and we can also, we have learned the Stokes law, Stokes theorem. Okay, we can write down this line integral to be a surface integral, and that surface integral is really the core of the field B. Okay, and now if you compare these two, okay, what do you find? That is del cross B is really equals to mu 0 times J. Okay, so this is also, Ampere's law. Okay, but it's just written in the differential form, just like what we wrote for the Gauss's law. If we write it down in this differential form, we have del dot E equals to rho divided by epsilon 0. Okay, so this is what we have. Okay, so when I try to derive this Ampere's law, so here I just assumed is a straight line current. Okay, in the real examples, it may not be really be just a straight line currents. Okay, it may be, all different formats. Okay, so the way to do it, I just want to quickly, I will skip some technical details, but we can derive this Ampere's law from in a more general way, using this Biot-Savart law. Okay, so the way we do it, let us consider a very general case. Okay, we have some volume here, we have some region here, and we have some, volume current density, and we wanted to calculate, so here is really R prime, and we calculated the magnetic field at a position R. So the way to do it is really, BR. We use this Biot-Savart's law. We have J, this current, times this cursive R direction. So this is cursive R. Okay, then times D top prime. Okay, so this is just, how the magnetic field looks like. Now what we do is, let us first look at del dot B. Okay, and see how it looks like. So then of course, we just need to apply this del dot this. Okay, so we put it as really J cross R hat, cursive R hat, cursive R square, d prime. Okay, d tau prime. And this one, to do this, we have to find some vector identities. Okay, so this one, you can find from the second page, from the formulas that are listed on the second page of Greenfield's book. Okay, so you can think about that. This is a vector A cross a vector B. Okay, so del dot A cross B. Okay, so you can look at Greenfield's book. Okay, so this whole things, okay, will becomes is cursive R hat divided by cursive square dot del cross J. Okay, minus is J dot del cross hat square. Okay, so this one becomes the two components. Okay, so what we have is we have the current. Okay, so here is so we have we have to be careful here. We have del, which is really partial over partial x, partial over partial y, partial over partial z. Okay, we also have del prime, which is partial x prime, y prime, and z prime. Okay, so here is kind of to this test charge, is this position with respect to this, while this one is respect to kind of the source. Okay, and the current, okay, J is really depends on R prime. Okay, it doesn't depends on x, y, z. That is R position. So as a result, this one becomes 0. Okay. And this one, what do you see that this as I said is basically R hat divided by R square. Okay, so you can see that this is a function of R. Okay, del cross a function. Okay, that only depends on R. Is a function only depends on the radius. So that means this kind of a function we know from the directly from the picture, we know that this should have a core of 0. Okay, so this one should be 0. Okay, and now from all this you know that is del dot b should equals to 0. Okay, so this is how we calculate del dot b. Okay, and now we can also del cross b. Okay, so this is maybe before I wanted to say that, so we have really concluded is really del dot b equals to 0. So this is a lot like electrostatics. Once we have a row, we have some charges there, it will create the magnetic electrical field. But for however here it really means there are no single charge, like magnets. We often have the south direction and the north direction. Okay, so like charge, we have positive charge and a negative charge. However, for the magnetic field, there are no such things, just like electron, we call it a monopole. Okay, so if give you a magnet, if you divide it by smaller components, then each small piece will still contains the south pole and the north pole. Okay, so you will never be able to find a magnet, for example, only contains just the south pole or the north pole one. Okay, so that is what we said. There are no such things called a monopole that we currently see in our nature. Okay. Okay, so this is just what is what this really means. It really means there are no magnetic monopole. Okay. So now let us look at del cross B. So we will do it exactly the same thing. The only thing, of course, original is del dot b. Now it becomes del cross is a times b. Okay. Okay. So this one, I just wanted to say that this del cross is j times r hat, cursive r hat, where it becomes j del dot cursive r square minus this j dot del cursive r square. Okay. Okay. So I will not really talk about talk too much details. You can look at the lecture notes, and it turns out this one, the integral will later becomes zero. Okay, we can convert the volume to integral, later to a surface integral, and we can consider the surface to be extremely large, and so that the current on the boundary becomes zero, so that the overall contribution when we do the integral. Okay, so of course this is not just zero. Okay, so this is really later we do the integral. Okay, and this contribution becomes the total integral becomes zero. Okay, and this for this integral, so you have to remember that this is really give us the the Dirac delta function. So this one is really give us 4 pi. Okay, del cross 4 pi times this delta function, at this cursive r point. Okay, so at the end, if you put these two pieces together, so 4 pi. Okay, and then you have this j, which is the r prime direction, times this del 3. Okay, delta 3. This one is really r minus r hat. Okay, because that is the definition of the separation vector. Okay, then times d top prime. So what do you see that this we said that this integral will just really give us the value of j at this r position, because this function is really means it is zero everywhere if this one is non-zero. Okay, and this integral becomes 1 when r equals to r prime. Okay, so at the end we just have this. Okay, so that really give us mu 0 j. Okay, which is really just the formula that I described here, for this simple straight line current situation. Okay, so in other words that we kind of derived this Ampere's law. Okay, we really have this del cross b equals to mu 0 j, and if we do this integral, okay, b dot dl, okay, this integral will equals to mu 0 times the current that are enclosed inside this loop. Okay, and you can see that this Ampere's law is very similar to the Gauss's law. Okay, so in other words that we start from this Biot-Savart law. Okay, we derived this Ampere's law. Okay, just like previously we used Coulomb's law, and we derived the Gauss's law. Okay, so they are very similar to each other. Okay, so next lecture, I will discuss about more examples, how to use this Ampere's law. Just like Gauss's law, Ampere's law is always true. However, it is also not that always useful. If you have problems, that we often handle if there are a lot of symmetries there, like infinite straight line, infinite planes, infinite solenoids, or or some toroids, we can use these symmetry reasons to figure out the directions. So we don't really need to do the these vector integrals here. Okay, but as I said, Ampere's law it only works best if we know its symmetries. We know the problem have these symmetries. But if the problems that we need to handle doesn't have these symmetries, then it is often difficult to apply this law to solve the problem.